right. Hello, everyone, and welcome to Historical Geology 1404. It's exciting. We made it through 1403. Who had fun in 1403? Okay, I didn't ask if you enjoyed the whole class. I'm asking if you had fun. Okay, you still don't have to raise your hand, but I would appreciate honesty, right? But yeah, 1403 is fun. Hard. Who can agree it was hard? Yes, everyone can probably agree that it was hard. And I absolutely acknowledge that. Who was it that showed me, what was that website we looked at last?
The Rate My Professor.
Rate My Professor.
It was me.
Yeah, that was you. That was you. I thought so. That's why I was looking over there. She showed me this website called Rate My Professor where people can leave reviews. And most of the reviews were good. And almost all of them said his class is extremely hard, but he makes it fun. And I'm just like, such a win. That's a huge win for me. I love that. I want you to get stretched. I want you to get challenged. This is how we grow muscles. Your brain is no different. Your education, your knowledge is no different. I aim to not only teach you knowledge, but how to gain wisdom as well by figuring things out for yourself. Do you know the difference between knowledge and wisdom, by the way? Knowledge is just, it's stuff, it's facts. Wisdom is how you apply it, right? It's a big part of what science is. Here's a fun way to break it down. Knowledge is knowing a tomato is a fruit. Wisdom is not putting it in a fruit salad, right? You remember that now. It's going to stick in your head. Okay. So, here we are, 1404. This is historical geology. So, you learned about what makes our planet and the processes that happen on our planet in 1403. Now in this class, we're going to cover some new stuff over 3 modules. Okay. The first module is, to be honest, a lot of review from 1403. And the reason why is because I have students here who have not taken the class in a little bit. I think, let's see. Joel and Alma, you took it in the fall, right? You took it what? Of the fall, yeah. Right? Joel, you took it in the fall as well, right?
Yes.
Yeah. So I don't think I have anyone in here who took it further back than that, because the rest of y'all I just had in the last 8 weeks. But occasionally I'll have students that take this class, and I may have some online students doing this, who took 1403 a year ago, right? Sometimes. It just depends on how their advisors set up their classes. So, and because the knowledge of 1403 is prerequisite to understanding 1404, the first couple of weeks of the class is going to be some review, okay? The first 2 weeks of this class are going to be a lot of 1403 review with some new, fun, interesting stuff sprinkled in there to make it, at least a little interesting for those of you that just took the class, okay? I'll apply it to some new things, okay? Starting in Module 2, that's when we really hit the new stuff. And that's when we're going to talk a lot about biological principles. If you haven't taken biology, no worries. I'm not going to go super deep on it. In lecture content, you guys know me. I'm going to go off on these weird, random, super deep tangents. There is no helping that. I know myself, and you know me by now, right? That's just going to happen. And please feel free to ask questions. I love our conversations. But I'm going to discuss some fundamental biological concepts. We're going to learn a bit about genetics, how that works, mutations. We're going to tie that into evolution. And that's going to help us establish the history of life on Earth and how we can study that using things like fossils and chemical clues left behind by life here on Earth over the billions of years. And then after that, we talk a lot about the geologic timescale. Okay, Module 3 is going to be all about the geologic timescale. We ran through that really briefly in 1403. And I will refer to it in Modules 1 and 2 here on 1404, but Module 3 is when we go through it piece by piece and we discuss all the major biological and tectonic events that occurred during each of those time periods. So you have some general knowledge of how things progressed over time here. Okay, so historical geology is all about taking the ways that you've learned to interpret science in 1403 and tying it back into the interpretations we've made here in 1404, okay, using the things that you learned. Does that make sense? Great. Let me just breeze through a couple of these. You're familiar with pretty much all this stuff. Please email me. Do not send me messages on Blackboard Messenger. Those of you that did send me messages, whenever you took 1403, you may have noticed I took a little longer to respond to those. I don't get a notification when you send me something there. If you send me an email, boop, it goes straight to my phone, and I'll email it as soon as I have a chance. If you send me a message over Blackboard Messenger, it just sits there until the next time I log into Blackboard and happen to look at the Messages tab. Don't do that if it's an answer you want right away. Okay? Let's see. What else? There is no required textbook here. You guys are familiar with this. I don't actually have, so for 1403, you probably used that website that I made. Maybe you did, maybe you didn't. But there's a website dedicated to 1403 that hosts the textbook and everything on there that you can use if you want. In 1404, I don't have a website. I have the goal of making one like I did for 1403 someday, but I have so many other things going on. It's not going to happen right now. But there is a PDF version of a textbook that you can use as a supplemental resource on the Blackboard page. You can download that if you like. It's open resource, not charged for it. I got it. I think the University of Queensland wrote this one over in Australia, and they let me take a PDF, and they said, yeah, you can share it with your students. So it's there as a resource for you. I do not pull information from that textbook. As always, what I teach you is your first resource. Any textbook or online thing that I give you or that you find for yourself is supplemental to me. Okay? All right. Because of the odd events that occurred this morning with the story that I told you all a little bit ago for online students, there was a bit of a kerfuffle at the gym this morning while I was there that I had to deal with. I'm going to be finishing my breakfast this morning while we talk. Hope you don't mind. Class schedule is going to be pretty much the same. 1403, 8 weeks, 5 labs, same schedule, twice a week, a couple of exams, one at the end of every module. Final exam is cumulative. Same rules apply. Extra credit for notes. Try and put together a fun geology movie night like I did last time. Okay? Or maybe it'll be movie night. I don't know. Did you guys like having it during the class period? Yeah, you did? Maybe we'll have it during the final class period again this week or this 8 weeks. We'll see what happens. Last week or last term, some weather messed up some of the schedule. Those of you that were in my Monday, Wednesday class last term, you know the weather really screwed with us. We'll see what the weather does this year. Maybe we'll have to, or this term, we'll have to see what happens. We might need that extra day. All the same course objectives here for the most part. All of the same standards apply. No cheating. That means no use of AI and things like exams. AI is an excellent tool to use as a, how do I put this? A manager of information. Not so much a, I wouldn't trust it necessarily as a purveyor of information, a source of information, okay? Because how many things can you really, truly, 100% trust on the internet? There's not a whole lot of stuff on the internet that I would say you can absolutely trust. And what AI does is it scrapes all the information and gives you an answer based off of what it finds. So if we assume that 50% of everything on the internet is true and 50% is not true, because people can post whatever they think is true or whatever they want to there, and AI doesn't know how to tell the difference, and it gives you an average answer based on that 50-50 split, then it's kind of a toss-up whether or not what you actually get from AI is going to be accurate. The best way to use that is to give AI a very specific prompt for what you're looking for, and then it can give you a source. That's how I personally use it. Now, do not use AI on anything that has a summative experience. So exams are a summative experience. That's a way for me to determine what you use, or how, what you understand, okay? What you have acquired, the knowledge you gain. Using it on things like labs can be useful, but again, if it's giving you the wrong information, you're going to get the answer wrong. So that's why I say everything, including AI, is supplemental to me. Take what I teach you as the primary source. Okay? So, none of that, copying answers, plagiarism, none of that. Please, if you suspect that something might be plagiarism, if you're worried it might be, always ask me and I will tell you. Please keep your phone use down in the classroom. I personally, I don't have my phone on me while I'm in here. I'm respecting the time that you guys give me to teach you, and I only ask the same. Unless there is an emergency, please do not use your phone. If there is an emergency, and you need to step out to answer a phone call, if you are one of my high school students, you are required to stay within line of sight of me, and you are not allowed to leave campus without telling me and your school. Okay? And your school, if you've been summoned by a parent, they can't just call you and say, hey, I'm picking you up. They need to call your school, and then your school needs to tell me that you are being legally and lawfully released. Okay? I used to be way more lax about all this. I've had my ears chewed off enough times that I can't let it slide anymore. So, and for that same reason, you guys know this by now, I can't let you out super early. If we finish class super early, you have to stay here for pretty much the whole duration of the class period. For my high school students, my older students, you are not being held to that same requirement. Okay, any questions before we jump in? No? Does anyone feel like reading out loud? Who wants to read something for me? No one's feeling bold this morning? My goodness, do we have to get through the awkward phase again? Alright, fine. I'll read this one. You're on notice, though. I might call on someone next time. It is interesting to contemplate a tangled bank, clothed with many plants of many kinds, with birds singing on the bushes, with various insects flitting about, and with worms crawling through the damp earth, and to reflect that these elaborately constructed forms, so different from each other, and dependent upon each other, in so complex a manner, have all been produced by laws acting around us. My friends, this is what we call a run-on sentence. But aside from that, what does it mean? Charles Darwin said this. Origin of Species. Fantastic book.
So we're just kind of talking about how like all the animals and stuff, all the insects and everything kind of came to be just by governed by like laws of science that we know to be true.
Yes, they came to be by the laws of science we observe around us. That's one of the very good observations. What's another one here? Not only that they came to be, but what else?
Dependent upon each other. Think that how they expanded, evolved.
Overnight oats are so conflicting. Do I swallow it? Do I chew it? I don't know. Somewhere in between. I was asking you to expand your answer a little bit there. You're right, they are dependent upon each other. But what does that mean? A cycle. Many cycles. Food cycle. Right? Waste cycle. So many cycles. The rock cycle, the water cycle. All of those cycles, which we learned about in 14.3, are dependent on each other. And guess what? So are biological cycles and processes. Yeah, what's he observing here? The things we take for granted. Like if you're just walking along the street, just going for a walk, just kind of like kicking a rock around, oh, it's kind of pretty. If you take a second and you look at it, all of the many faceted biological and geological processes going on around you that are codependent on each other, that's what he's observing here. Highly recommend reading this book. Some of the concepts in there are outdated, sure. He wrote it a long time ago, but it's still an incredible book to read, especially if you're interested in something like biology. Okay. A little bit of a flex here. I collect books. I find really good, high quality, usually leather-bound, signed versions of books that I really like if I can find them signed. And then I'll acquire them for my collection. I have quite a fun collection of books at my house. One of the ones that I got about a year and a half ago, I got The Last Harvard leather-bound, like Harvard edition leather-bound copy of The Origin of Species on the market. Somebody was selling the last copy of it, and I managed to snag it. So proud that I got that. I love that thing. It's so pretty, so cool. But you know, if it's a book that means a lot to you, it's worth having. Okay, so why do we study geology? Well, you've kind of become familiar with the fundamentals of geology. What value is there in geology? Aside from what you see here, you can elaborate on those if you want, but I'm curious now. You've taken 8 weeks of geology. What value is there that you have found in studying geology?
Josh,
Yes.
when I went to Rio Dosa, when I was standing on top of the mountain, all these Josh-like thoughts were coming to me, and I told my mom, I said, this is all Josh's fault, I tell you right now.
Oh, music to my ears.
Because, I was like, and you see how the sediment of it, and I was like, all right, I need to shut up right now.
Make your mom fall asleep and fall off the mountain. No, that's great. I love that. Josh-like thoughts. Has anyone else had Josh-like thoughts since taking my class? No one else will admit it.
No, I will admit it just
Thanks for speaking up. I really appreciate that, actually. Side note here. So, I am in the America's Favorite Teacher competition this year. I don't know if you guys have heard about this or not. It's something that's gone on for a couple of years now. I was told I should be in it, so I'm in it. And it's a vote-based thing, so I'll send out a link later if anyone feels impressed to vote for me. Please feel free. I'm not going to be one of those teachers who's like, vote for me, vote for me, vote for me, vote for me. I'm not starting a TikTok and dancing on trends, to make people vote for me. I'm not going to be that guy. I'm just going to keep doing my thing, and if people want to vote for me, they can vote for me. Right now, I'm 4th out of 80 people in my group, which is pretty cool. If I make it, great. If not, I won't. But I'm giving a shot at it. So if you feel like voting for me later, please feel free to. But that is definitely something. That is definitely a story that I would share with. Because every now and then they'll send out like, "Hey, what's a favorite teaching moment?" That made my day. Thank you very much. That's really all I want, guys. I want to change the way you think. I don't want to change the career that you have. I don't want to change fundamental concepts of your personality. I don't want to change religious beliefs. I just want to change the way you think about your world. That's it. Okay? So why do we study geology? So we can look at and appreciate and attempt to understand our world better. That's what it comes down to. Now, for the purpose of continuing the slide forward, there are a couple of other things we're going to look at. We want to understand the world we see today, right? What does that mean? What's the value in understanding the world we see today? That kind of ties into something we discussed in the past, the principle of uniformitarianism. Who can remember what that is? I hope you have your 1403 notes because they will be relevant.
Do you need it like word for word? Or?
Word for word is how I asked you to remember it. If you remember it word for word, good on you. If you can give me a basic summary, we can go off of that for now. That is dynamic. Mm-hmm.
Physical, chemical, and biological laws that operate today also operate in the geologic past.
Physical, chemical, and biological laws that operate today also operated in the geologic past. Absolutely true. What's the next bit, though? If they operate today, and they operated in the geologic past, what's the next logical conclusion? They will operate in the geologic future, absolutely. So what's the value in understanding geology today? We piece together the parts of our past and can, to an extent, forecast what may occur in the future geologically as well. We capped off 1403 by learning about earthquakes, right? We learned about earthquakes and tsunamis and all sorts of other natural disasters. We can understand the pattern of those things, the way that they have occurred in the past, the way that they're occurring right now. We can be pretty certain in being able to forecast the way they occur in the future. That's just one tangible benefit. Okay? It helps us to predict what Earth will look like, that future component here. Here's that fun, 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 here's that f what do we call us? Supercontinent. Okay. Lots of potential supercontinents out there that people float around pictures of, images of, and it's all models. Okay, I've used that word model with you guys a few times. A model. I've shown you models, predictive models of the way that things work in nature. In science, we use models a lot. It's really the only way that we have right now to graphically represent what we're talking about. A model is essentially a way of taking an equation and translating it to a visual format. Okay? But here's the thing with models. They are based upon data sets, and data sets can be flawed. So whenever you look at a model like this, think, that is a lie that may contain some potential truths. That's the way I look at models. Okay? Every model is just a lie that may contain potential truth. Some of this may be true. Is it likely that all of it is true? No. But I acknowledge that some of the truth, some of the data involved here, they lead to accurate things. It's just the best thing that we've got right now. Okay, the best way to represent that, the data that we collect. Now, the other big reason that we talked about was valuable resources. There are lots of resources in the ground that we only know the existence of, or how to find, or how to get, or how to process, how to use, because of geology, right? How many of the resources did we learn about last term in 1403 that are vital to your everyday lives? Name me some resources that come from a geologic foundation, a geologic source in your everyday lives. Louder. Water. What else? Genesis, what's a resource you use in your everyday life that comes from a geologic source? Metals. Perfect. Like aluminum. Fantastic. Coal. Can you think of one? Oil. Good. I was hoping you would say coal, but that was kind of a gimme, but yeah, it's okay. Oil. Yeah, absolutely. Energy. What else? Huh? I mean, yeah, there's lots of agricultural resources we get for that, but Plastic. What is plastic? We had this whole conversation about what plastic is during glaciers, right? What is this material that we call plastic? Do you know where plastic comes from? We take it for granted. But do you know where plastic actually comes from? Plastic is everywhere. Look around, find me something that doesn't have some kind of plastic in it. Most things in our world have a lot of plastic. Why? Well, because it's moldable, it's shapeable, we can make it do whatever we want. Plastic is the byproduct of refining oil. Did you know that? When you refine oil, you get crude oil out of the ground. This is crude oil, if you've never seen it. Look how viscous that stuff is. It's like black syrup. That's not what we put in our cars, right? That's not gasoline. How do we get from this to gasoline? You have to refine it. That means removing all of that black tarry stuff and leaving only the gasoline behind. When I refine this, I would get about that much gasoline out of it. So what's the rest of that? That gets siphoned off and becomes a sort of slag substance, okay? And that gets turned into plastic. Plastic is made from the byproducts of hydrocarbons, which, is another complication to the whole shut down the oil field campaign that goes on. Would it be great if we could have a 100% clean energy substance and not have to rely on oil? Sure. Do things like that exist? Absolutely. Talk more about that in a second. But what happens if you shut off the oil industry? You also shut off the plastic industry, right? Is that the worst thing? Plastic pollutes our planet. It takes forever to degrade. Well, aside from the whole convenience factor, look around you at what is made out of plastic. My bottle, that case, the top of this counter, right? All the things that are now made out of plastic. Do you know what those were made out of back before we had a lot of plastic? Wood. You stop making plastic, you gotta start chopping down more trees to make the stuff that currently is made by plastic. No matter what, it's not a clean answer here, right? That's what I'm trying to get you to think about here. Think a little more deeply about these things, okay? As far as clean energy sources go, just a moment on that. Can you think of any 100% clean energy source? I'm talking about a source of energy that produces more energy than it takes to put in, right, to start the process, and is capable of no byproducts. Can you think of one? No?
Everything or something. I mean, nuclear, like the whole argument of like the byproducts and stuff, they cost billions of dollars to put in.
Ivan and I are both big proponents of nuclear energy. We've talked about this, right? So I think that using nuclear is great. But there's absolutely byproducts, right? A lot of energy is lost through that process. This waste heat, and unfortunately, the irradiation of materials. And what do you do with the fuel after it's spent? You got to put that somewhere, and it's going to pollute places that it gets put unless you're very careful with it. So there's some complications there, and it's not 100% clean. Very clean if you are careful with the procedure for disposal. Not 100%. There is something that comes along with every energy source. There is some cost. There is some complication that you got to deal with. Okay, so as much as the fossil fuel industry is not ideal for the environment, we are not at a technological place right now where we can really go much further than that. At least not without massive adoption of nuclear energy. And even then, like I said, there are complications. But even all of these energy sources come from the ground, right? At some point. Okay. So, just reviewing some of the stuff we talked about in 1403. I mentioned that we were doing a lot of review for this first module. So if this all sounds very familiar, that's why. But it has been 9 weeks since you got this content, so it's probably good that you're getting a refresher. Anyway, Earth is dynamic. Alma mentioned this earlier. Constant changes in our Earth, right? Constant change in activity. Some examples I have up here on the board. But we learned about some other examples. There's the big stuff, the obvious stuff, the earthquakes, the tectonic plates, right? But there were some other things we learned about in 1403 that were aspects of the way that the Earth constantly changes. What were some of those? Yeah, what were some of the other aspects of the way that the Earth changes? The ways that we learned about in 1403. Now that you've made it through 1403, you learned a whole lot of the ways that Earth changes. The processes are constantly going on. What are some of those?
Like the ocean activity.
Sure, yeah, ocean activity, weathering caused by the ocean, weathering and erosion, yeah, those processes we absolutely talked about. Fantastic. What else?
glaciers and stuff too.
Glacial movements, yeah, that slow grinding of that ice against the rock, pulverizing it slowly over time. Great. So dynamism doesn't have to be fast, and as a matter of fact, it often is not. Long-term processes cause more change than the shorter-term ones a lot of the time, right? Trillions and trillions of tons of rock moving 5 centimeters a year. That's tectonic plate, right? That's going to create a heck of a lot of energy and destroy a whole bunch of material, rock material, and make new material and all the other things that our plates are doing, right? So things like the formation of rocks, liquefaction, we call that, right? The sedimentary rocks, the erosion of material, those are other things, okay? So you've got those big scale and those small scale events, and all of them add up to this massive dynamic world we have now. Now, all of the changes which we observe in the world, we have the tools to observe now. We did not always have the tools to observe these worldwide events. We can look at, pick your local or your favorite news network, and you can see what's going on with the war in Iran right now, right? You can look and see that there was an earthquake in Guam or Taiwan or any number of other things around the world. It is so easy to share information and see what's going on in our world right now. It wasn't always like that. The world used to feel a lot smaller to people because they were in isolated communities and there was no such thing as global communication. So what do you do then? How do you answer these questions? How do you ask these questions, right? Well, that's where these fathers of science come in. Maybe you'll recall I told you about this guy named Aristotle, right? Do you guys remember some of the examples I told you about the questions Aristotle asked or was asked and he came up with answers for?
Oh, skeleton, fossils and stuff.
Yeah. People would bring him fossils, like a fossil fish, and he would come up with explanations for that. Now, he didn't have the knowledge we do now. He didn't have the global communication we do now. He didn't have a library of books, at least not like we do now, right? He didn't have the internet, right? He had more or less common sense. But what is common sense? Sense dictated by common perspective, right? What we call common sense, don't run someone over with your car. Why is that common sense?
Just don't do it.
Right, we don't do it, and we think of it as common sense, but why is it considered common sense? Because you know what's wrong morally, because society has dictated it thusly. Also, it's against the law and there will be consequences, right? You don't want to face those consequences. Even if you really hate a person, you don't run them over, most people don't run them over with a car, right? Every now and then there's some outliers and people are like, screw the consequences, I really hate that guy, right? And they face those consequences, but common sense dictates or states that you wouldn't do that. But what if common sense is different? What if I'm talking about a guy 2,500 years ago? Was common sense the same thing back then? No, not really. Common sense then, and where he was living in that part of the world, said, hey, there's this pantheon of gods that control everything in our world. Everything that happens in our world, these dynamic things we observe, is because of the influence of some god or another. And they would justify it that way. If there's a massive storm in the sky that wreaks devastation on our civilization down here in ancient Greece, it's probably because Poseidon and Zeus were having an argument up on Olympus or something like that, right? That's what common sense was back then. And that's how they attempted to answer these questions. Common sense has shifted as society has shifted, right? And no doubt will continue to shift over time. Perhaps the things that we consider common sense now Other people in 1,000 years will look back and think, oh, those silly people. Common sense. Sure. Right? But that's where we are. So, but the value in what these natural philosophers did thousands of years ago was in asking the questions. Never, ever be afraid to ask questions, my friends. Asking the question is the necessary first step. How often do I ask you guys to ask questions? Or do I beg you to ask me questions? All the time. Questions are so important in my classroom and in life in general. Okay? Ask those questions. Learn to be comfortable with asking questions. It'll take you far in life, I promise. Okay? All right. So then, moving on through time, we had these more religious-oriented people, more, I should say, Christianity religious-oriented people. Okay, so like James Ussher in the 1600s attempted to use the Bible to explain how old the Earth is. Now, there's value in that too. He is attempting to answer a very important question. How long has this planet been here? Now, did he do it with a certain agenda in mind? Yes. His agenda was to prove that the Earth was made by a deity. Again, I'm not going to comment on people's personal beliefs. But that was his intent. I'm going to use the Bible to figure out how old the Earth is, and therefore attempt to prove that a God made it. Okay? So, what he found was, if you take all those dates in the Bible, you come up with the date of creation being October 22nd, 4004 BC, and I want to say it was somewhere around 9:30 a.m. when he said. I don't know where he got the time. I honestly don't even know where he got the day. But 4004 BC, sure, you add up all of the ages and the approximate lifetimes in the Bible where when it says, sure, you can end up with that, which is where the common Christian perspective or belief that the Earth is 6,000 years old, that's where that comes from, was James Ussher's study here. 1600s, this caught on so fast. Christianity was spreading throughout the world. Why? Colonization. In the 1600s, everybody with a navy was colonizing everywhere. Okay? This is where the beginnings of that global communication network came in. Now, did it take a year for a message to travel by boat from Jamaica to India? Sure. Sure. But that message could go. There was an established network. Okay? The world began to feel smaller, more connected. We began to see more of the things happening around the world. I'm using the royal we, obviously. I wasn't around. Okay? But humanity began to observe things, right? News of a volcano erupting in Indonesia would eventually make it to New York State, right? This is where we are. The establishment of these global communication networks, and the more they became established, the wider they got spread, and the faster that line of communication got, the more aware people became of their world and the ways it would change. The perspective of Earth dynamism began to grow. So people began to ask questions. Well, okay, if the world is that old, then how do you explain this? Things like that. And so the perspective of catastrophism came. It largely went. The perspective that these large things in the world are made by massive catastrophic events, mountains, valleys, the formation of oceans. All of these things happen because of giant floods, because of earthquakes that rip holes in the ground and make your valleys. All of that, mountains being raised over the course of a day or even a few hours by giant earthquakes. But as our global communication network spread and got faster, people began to realize those large, massive events, those aren't happening. What do we see? We see pretty big ones. We see a big earthquake, but there was no mountain that came out of it. Or there was no rip in the ground that turned into this giant valley. What do we see instead? We see the slow, gradual changes, day by day, year by year, decade by decade, that eventually, once you watch long enough, make a change. And this is where Hutton comes in. So this is James Ussher, by the way. This is where Hutton comes in. Okay? Hutton and other geoscientists, like him, scientists in general, not just geoscientists, but other scientists, and he began to record these observations, these long timelines. If this happens over this period of time, Multiply that by X amount of time, and you end up with this feature that we can observe as existing. Let's think about this logically, right? If I know by my own 2 eyes and observations that it takes a year for X to happen, and I see something over here that is X times 1,000 in size, the logical conclusion is that however long it took over here, a year, 2 years, 10 years, for X to happen, this thing must have happened over 1,000 times that. We have the evidence of the result and the observation of the process. What's in between? Interpretation. And that's where people actually began applying modern day scientific principles. Experimentation, observation, falsification. Develop your hypothesis, attempt to prove it wrong. Succeed in proving it wrong. Or fail. You fail, you get a theory. Fail enough times, and your theory eventually ascends to a higher plane, you can think of it. A theory which has either been proven correct or is impossible to disprove, no matter what you do, is sometimes considered a law. But even laws, we find at times, can be a little wibbly wobbly. Even today, in our modern day age of science, we're beginning to understand laws differently. Law of gravity. What is the law of gravity? Gosh, we've talked about gravity in my classes a lot, haven't we? It's a fascinating subject. Did you know that there are four forces in our universe that dictate the movement of energy and matter? Maybe you've heard of these. Strong nuclear force, weak nuclear force, electromagnetic force, and gravity. Ah, but wait. Now we have the technology to understand, to study gravity even more. We're beginning to think gravity may not actually fit in that club very well. Gravity may not be so much a force over matter and energy as much as it is the way that matter and energy interact with space-time. It's so weird. So what my point here is, even things that for a while we have treated as a law can still someday change as technology changes and our ability to understand and comprehend things change in our universe. Okay. All right, so Hutton established that principle of uniformitarianism. Okay, where you have physical, chemical, and biological laws that operate today, also operated in the geologic past, and, my little addition there, will continue to operate in the geologic future. There's another addition on top of that I told you about last time. That'll come into play later. Okay, moving on. You guys remember our exercise about how old the Earth is? Do you remember, where is it? Yeah, this. You remember this? Okay, well, let's, you guys remember. I don't need to be as dramatic this time around. Okay, but how many dots were on this piece of paper? Do you remember that? 1,000?
5,000.
Oh, it's somewhere between 1 and 5,000. I will give you that.
3,000.
Above 3,000.
4,000.
4,000. Yes, this piece of paper has 4,000 dots on it. Now, how many of these sheets of paper do I need to reach 1,000,000?
250.
250 sheets. Thank you. Each ream of paper has 500 sheets. How many sheets to reach 1,000,000,000? You just multiply 250 by 1,000, you get 250,000 sheets. That's going to be 500 reams of paper. That's going to give you a tower of paper 83 feet tall. It's about a 7-story building, give or take. Okay? Now, that's to reach 1,000,000,000. We want 4.5 billion, which is the age of the Earth, right? We're going to get a tower of paper 380 feet tall. It's about 35 stories, give or take, depending on construction standards. Okay? It's a pretty tall story pretty tall building made entirely out of paper. Each sheet of paper has 4,000 dots on it, and each dot represents a year. That's how old the Earth is. The other example I like to give, walking around the equator. Wait for it. What a time to be alive when technology can't keep up with the speed of me. There it is. All right. We're going to go for a walk around the equator, and when we do, we're going to take a certain number of steps. It's going to take 15 times around the equator to reach 1 billion steps, and 70 times around the equator to reach 4.5 billion steps. Right? Kind of puts it in a good perspective for you. Earth has been around for a while. Earth is about 4.5 billion years old. The Sun, about 5 billion years old, as far as we can tell. Our galaxy, a little before that, maybe 5.5 billion years old, as far as I'm aware. Our universe, 13.7 billion years old, as far as we are aware. Yeah.
Never mind. I don't know. Do you think that's a real time because of like how time and speed work together?
Gosh darn it, man. You trying to derail me? Alright. His question was, do we actually know if that's true because of how time works? You are so right. We say that the universe is 13.7 billion years old because that's the furthest that we can see the light. And when I say light, I'm not talking about a visible spectrum here. I'm talking about radio. Do you guys know that radio, what we call radio waves are actually, it's in the same spectrum as light? Yeah. Radio waves are the spectra that travel the furthest through space, okay? So when we say that the universe is 13.7 billion years old, what that means is what we perceive as the outward edge of our universe, the radio traveling back to us from there has traveled 13.7 billion years to reach our stuff here, okay? This is kind of how we know we're not at the center of the universe. Sorry, you aren't at the center of the universe, right? I know. About the time you turn 16 is when you start to realize it, okay? So, we aren't at the center of the universe because we can see light traveling from X distance that way and double X distance that way. If we were at the center, we would see that light from the edge of the universe reaching us all at the same time. Instead, we see closer over here, further over there, so we know we're not at the center. But we're seeing light, radio waves that travel 13.7 billion years to reach our detector, okay? But light can only travel at the speed of light.
It doesn't like the constant expansion of the universe kind of like
The universe
that we'll never know.
The universe is constantly expanding, my friends. If it weren't, then we would all still live in a pinprick. The universe began, the Big Bang began with an explosion of matter from an area about the size of the head of a pin. We don't live in the head of a pin, as far as we're aware, right? We live in a universe, and it's constantly expanding. It has to. This ties into things like entropy and the loss of energy over time. We won't go into that, okay? Because the universe is constantly expanding, and the oldest light that we have received, the oldest radio we've received is 13.7 billion years old. That's how long it's been traveling through space. The universe is actually probably much bigger than that. We just haven't received the light from it because it's constantly increasing. Yeah.
And technically, won't we like never receive that light because of how fast space is expanding?
Yeah, it's expanding at a certain rate. Light is traveling back inward into the universe from that expansion, the outer edge of our universe. And by the time that light reaches us, I mean, our civilization will have come and gone like a blip, right? We're only observing for a tiny, small period of time. It's super unrealistic to expect humanity to be around in 1 billion years to register light comes in from the edge of the universe then, right? Even if life is still around here on Earth, it will change substantially because of the nature of evolution, which we'll talk about later, okay? But the point being, we can only see the light that is 13.7 billion years old right now. Now, because we know that the universe is expanding, it's probably way older than that. Some people have estimated that the universe may even be as much as 40 billion years old. But the oldest that we have seen are the radio waves from the expansion at 13.7 billion years away. Light years away, so I should say. A light year is the distance that it takes light to travel in 1 year. Okay, that's what a light year is. When we say that something is X number of light years away, that means that at traveling at the speed of light, it would take us X number of years to get there. So our nearest star, Betelgeuse, somewhere like that, it's like 4.5 light years away. It would take us traveling at the speed of light 4.5 light years or years to reach that. We cannot travel at the speed of light. That is beyond our physical ability. The only thing that can travel at the speed of light is light. Traveling faster than the speed of light is a matter of conjecture. Some people believe we should be able to. Some people believe that there are actually ways that nature has gone around that already. There's this fascinating thing called the Schönhorn effect. It's purely theoretical. I'm not going to go into it, but it's ways that some people believe they have proven that you can accelerate things for just a brief trillionth of a second beyond the speed of light. But then there's the other camp of people who believe if you could go travel faster than the speed of light, then you kind of break the universe. So it must not be possible. Speed of light is the ceiling, as far as we're aware of how fast things can go. So if we ever do reach that point, I don't know. Right now, if we had the concerted efforts of every nation on Earth and we all cooperated, I am confident we would be able to build a vessel capable of traveling maybe 10% the speed of light. And it would take a while to get up to that speed. Basically, you need to accelerate it with as little fuel as possible. So you need to slingshot it, and it would need to gather energy around other planets, basically stealing gravity from that planet to slingshot itself further and further and further. And then eventually, you'd be able to launch it off somewhere at an extremely fast speed. But even at 10% the speed of light, it would take 45 years to reach our nearest star. That's where we are. You know what would happen theoretically if you went past the speed of light? You guys got me on. Ivan got me on this tangent. I'm sorry. It's his fault. It's his fault. But you know I love this stuff. It's okay. No, it's okay.
Sorry.
Sorry, guys. If, get this, okay? This is going to blow some minds here. If a light particle, and our time, by the way, is based entirely upon perspective of light, right? We measure our days in revolutions around the sun, right? We measure distance in space for how long it takes light to go from A to B to our perspective. But you know what? We've proven that the further you are, the closer you get to the speed of light, the slower time seems to go for you. From your perspective, light and time are interwoven with each other. So, for a photon that's emitted from a star, it takes about 8 minutes for that photon to go from our sun to Earth. For that photon, traveling at the speed of light, it's instantaneous. Immediate. Emitted here. Same moment. Because it's at the speed of light and therefore time doesn't exist to its perspective. So a star 13.7 billion years away that's just forming on the edge of our perceived universe emits a photon, and if it, by a miracle, it makes it here to the other side of the universe, instantaneous for that photon. So if time is at 0 at the speed of light, what would happen if you went past the speed of light? What do we think? I want to know what you think.
You could go back.
Ooh, she came down to the Star Trek answer. Good job, Genesis. Okay. Yes, this is what I call the Star Trek answer. You go back in time. What happens if you're traveling forward in a car and then you slow your speed to 0, you're not traveling anywhere. But then you go past that 0 in the other direction, you start going in negatives. You start going backwards, right? Negative time is back in time. That's the Star Trek answer. That's the notion, the scientific philosophy behind every go back in time thing in Star Trek and every other show that has time travel. Okay, you're going backwards in time because of that. But then there's the other camp. The other camp that says you cannot physically pass the speed of light. It is a barrier beyond which you cannot go, because if you did, you break causality. Do you know what causality is? It's cause and effect. For example, I flip the switch, that light turns off. There is a cause and there is an effect. That's causality. If you were, this other perspective on going past the speed of light states that if you were to go past the speed of light, you would break causality. Basically, things would happen before the thing that would have caused them in the first place. Yeah, a pen would fall from the air before I picked it up and put it here. So, those are kind of the two camps there. One of those two things would happen if you were able to go faster than the speed of light. Do I know which one is correct? I don't know. I am not a quantum physicist. I know enough about it to make a conversation like this and to share my excitement about it, but I don't know enough to be able to state mathematically which one of those is most likely. All right. Should we bring it back to geology? Bring it back to Earth? Okay, here we go. All right. So Earth, very old. Okay, but where do we go? Where do we get off measuring age, time like that? How can we measure that here on Earth? Well, there are a couple of ways that I taught you in 1403. Okay, there's the law of superposition. Anyone remember that one?
Younger on top of older.
Yes, exactly. Excuse me. Whatever is on bottom is older, right? Because things are stacked on top of each other like pancakes. When you go to IHOP and you order a stack of pancakes, they have to put them on your plate in a certain order. They are stacked on top of each other. Which one was there first? The one on the bottom. Which was the last pancake put there? The one on the top. Same with rocks. They are deposited. Sorry, I just bumped my microphone there. They are deposited on top of each other in the same way. Law of superposition states that whatever is on whatever's on bottom is oldest. Okay. Then there is index fossil succession, which allows us to look at the fossils that are present in layers of rock, identify them, and if they are index fossils, which is a concept we will learn more about in this class, they are easily identifiable. They can be used a lot of the time. I'll teach you about why here in a bit. Okay. If there are index fossils present, we can track the distribution of those fossils over distance in other layers of rock. So if I know that the fossils here in layer A are here, designating that as layer A, and then B, here's B, location 2 is like 100 miles away, location 3, okay, well there's nothing above A, but it might have just gotten weathered away, okay, and then location 4, wait, location 4, we go straight from A to C to D. What happened to B? It's gone, it's not there. For whatever reason, that environment that was there at the time that B was being deposited over here was not over here. Maybe B is a layer that was deposited on a beach. Further out that way, you go deeper out in the water. Further out this way, you go into shallower or into on land, and therefore there wouldn't be a beach further inland. Right? Whatever the cause may be, we know B isn't present here, and there's some interpretation we can make from that because of the lack of the fossils showing that B should be there. Okay? Okay. Then there is radiometric dating. You guys remember the concept of radiometric dating? Okay, I'll remind you in a minute. Okay? So, law of superposition. This is all relative. There are no numbers associated with the law of superposition. It simply states that A is older than B, is older than C, is older than C, is older than D, is older than E. So on and so forth. Like that stack of pancakes, like a stack of blankets, okay? then there's the fossils, okay? Now, let's talk about what fossils are for a moment. A fossil is a remnant of a living organism left behind. Okay? Now, is it the original body part? Not usually. It's been replaced by something. Does it have the exact same shape? Sure. Does it have the exact components? Rarely, but possible. It's mostly just been replaced, down to the cellular structure a lot of the time. Now, for this to happen is a process that typically takes about 10,000 years. As a matter of fact, people will often confuse paleontologists with archaeologists because we do a lot of the same stuff. We go and we dig up bones and we piece them together in labs and all of that. We usually cut off at about 10,000 years from each other. Anything younger than 10,000 years, a paleontologist will typically turn over to an archaeologist to study. Anything older than 10,000 years, an archaeologist will typically turn over to a paleontologist to study, with, a few exceptions in there. If anything is clearly, obviously related to human civilization, we'll still probably give it to an archaeologist, even if it's older than 10,000 years. If anything is clearly, obviously related to an animal that had nothing to do with human civilization, archaeologists will typically turn it over to paleontologists, even though it's younger than 10,000 years if it's a fossil, right? Okay. Fossils can include things like bones, the casts of burrows, footprints, chemical residue, poop. You know this fossilized poop? We call those coprolites. I have one in my display case out by my office. Okay, those are actually very useful. Okay, so this is a fossilized turtle shell that I showed you all a picture of before. I found that in Montana. These are fossilized trees, a few pieces of which I have up here or scattered around the room in my display cases. These are fossilized snail shells that I found here in Texas. These are actually pretty common because a lot of Texas has been underwater at different periods of time. Hello. All right, here we go. So, index fossils. It is useful to use fossils to identify layers of rock from each other. You can do it vertically, like we did with the law of superposition. So fossil 1, fossil 2, 3, 4, 5, etc. But also horizontally, over distance, not just vertical succession. Over distance, we can correlate this. So if I go 100 miles away and I find fossil 4 present here, or I don't find fossil 4 present there, both of those pieces of information give me interpretation information, data points I can use to interpret that past. Okay. Now, the requirements for being an index fossil, and by the way, index fossils is going to be a recurring theme here, so this might be useful to take note of. Okay. Index fossils need to have been alive for a short duration. Why? Because if they're alive for too long a period of time, they get less useful for differentiating smaller periods of time apart. So, short duration, say 20 million years. This layer was deposited, these fossils were alive over the course of, say, 20 million years. They need to have been present over, or there needs to have been a lot of them, I should say, okay? There needs to be a lot of them. Why? Well, because fossilization is actually relatively rare. You need to be in the right geologic conditions for fossilization to occur. You need to be deposited quickly, or you need to have been buried quickly. You need to have been buried in the right sediment. There needs to have been the right quantity of water present. You need to be encased in that sediment and in that rock before oxygen and bacteria can decay your body down too far, right? A lot of things need to work out just right. If we say that 1 in 50 million members of a species is fossilized, and then calculate in the likelihood that we will find that fossil, the numbers get astronomically small. So for us to have found, 1,000 T-Rex skeletons, I'm just throwing that out there, right? There must have been a ton of T-Rexes over the millions of years that they were alive, right? A lot, right? So it really comes down to a numbers game. The more individuals there are alive in a species, the more likely it is that we will find fossils of them, which means that they can be used as index fossils. Then they need to have a widespread habitat. Why is that? Well, it doesn't do as much good to correlate. It doesn't do as much good to use a fossil to correlate if it was only alive in one tiny little lake in the middle of Oregon, right? If it was, however, living across the entire equatorial region of the world, yeah, that's much easier, much better to use as an index fossil for comparison of layers of rock. And they need to have unique physiology. They can be somewhat similar, and because few species ever are wildly different from their relatives, they are going to be similar, but they need to have characteristics that make it easy to identify them apart from each other. For example, you can tell all of these belong to generally the same classification of organism, right? These are completely fictional, by the way. These aren't things that actually exist. These are called Caymanolophiles. This is from an exercise in genetic drift and variation that I had when I was doing my undergrad degree. Okay, I don't make you guys do that because I'm an expert at it. Okay, but this is an example of what I'm talking about here. They are all clearly related to each other, but different just enough that we can tell them apart. Unique physiology. So these are the requirements that you need. Make sure my camera is actually following me here. There we go. You still following me? Let me exit out of this real quick and make sure nothing's going on with this recording. There we go. Oh, look at this. When it goes blue, it's in follow mode. When it's green, it's locked in place. That's good to know. All right. Let's skip ahead to where we were. Boom, boom, boom. Okay. So all of these add up to making great index fossils, okay? So some common index fossils you're going to see me reference. Ammonoids. Very, very good index fossils. Long fossil record, but each species lived for a short duration. They were all over the world's oceans, and they're present through a lot of Earth's life history, okay? Brachiopods. Same thing. Present forever, literally tens of thousands of different species we've identified. Okay, now let's talk about radiometric analysis for aging. Who can remind me what an isotope is?
Is it the element, like an isotope of oxygen, which is kind of different number of like neutrons? Or
What about neutrons?
more or less like different.
More or less? Yeah. So this comes down to atomic mass, right? We have our atomic number here, which dictates the number of protons in the nucleus. And then we have the atomic mass right there, which dictates, well, the mass that's present in your atom. The combination of protons, neutrons, and electrons in your atom. Okay? So if I were to change the number of neutrons in my element, I would change the mass. And this is how you get an isotope. If you change the number of electrons, you get an ion. If you change the number of protons, you get a different element. You change the number of neutrons, you change the mass, and that gives you an isotope, okay? So isotopes are elements that have gained or lost neutrons to their nucleus and have made them unstable to an extent. There are some which we call stable isotopes, which a number of them still do fall apart, just not catastrophically so. They do change over time, just not catastrophically so. But then you have the unstable ones, which are catastrophically unstable. Okay, so an example of stable isotopes, 12, 13, and 14 of carbon. Carbon-12, that's your normal baseline carbon. Where's carbon? Up there. Okay. Carbon is right here. It has a mass of 12, meaning it has 6 protons, 6 neutrons. You change the number of neutrons by 1, you get carbon-13, an isotope. Stable. You add another neutron, you get carbon-14. Kind of stable-ish. I mean, it does eventually decay by losing those neutrons again, but that's a conversation for later. But there are isotopes that are defined as unstable. Uranium-238. Here's uranium right here, okay, in the actinide series of our periodic table. Uranium-238 is the normal version. If I remove 3 neutrons from this, I get uranium-235. Uranium-235 is the isotope which is used in uranium nuclear weapons. Uranium-236, which is slightly more stable, is what we use in nuclear reactors. Now, when something is unstable, it is going to bombard its area with particles. It's going to blast protons and neutrons and electrons off of itself until it reaches a stable state. Uranium is going to bombard its area with particles until it becomes lead-207. That's the next stable iteration that it will achieve. Now, any isotope of uranium will do this very quickly, but we found that if you have a certain mass of these radioactive isotopes, unstable isotopes, you can measure consistently how long it will take for half of it to decay into its respective daughter isotope, okay, whatever its stable variant is. We call this a half-life. It's the amount of time it takes for half of any amount of isotopes in a substance to decay. So for example, here I have a dinner plate of yummy, yummy, delicious uranium-235, okay? The amount of time it takes for half of that uranium-235 to turn into lead is 1 half-life. In the case of uranium, that is 703 million years. So after 1 half-life, I will have a 50-50 split. 500,000 parts per million of lead and 500,000 parts per million of uranium-235. What will I have after 2 half-lives? Yes. Of 750,000 parts per million of lead and 250,000 parts per million of uranium-235. Why? It's a half-life. It's always dividing the amount of available uranium in half. How many times can you divide something in half? Infinitely. And that is why this is a very useful method. Because if I just use some generic time measurement, like an hour, I will eventually go from 0 to 60, and the hour will be up, and that's how long I can measure a thing. But if I measure something by the number of times it divides itself in half over a given period of time, I can measure it forever. And this is the advantage of radiometric dating. Because there's no end to how many times those half-lives can progress. This is a very powerful tool. This is what allows us to say things like the Earth is 4.5 billion years old. Because we measure the ratios of the unstable original element to the stable daughter element, and that'll tell us how many half-lives have passed. Okay, that's radiometric isotopes. So, the oldest rock on Earth is 4.3 billion years old. That is this crystal of zircon from Australia in the Jack Hills. That's exactly what it looks like. That is a 4.3 billion year old crystal. But then how do we know that the Earth is 4.5 billion years old? Well, because we got samples from the moon. And the moon came from Earth. What happened here? The Earth was collided by a planet that was approximately the size of Mars, we believe. This planet was called Theia. So the combination of Earth and Theia colliding with each other generated a remelting of our planet here. Okay? remelted our planet here, and a whole bunch of debris got caught in Earth's orbit, and that debris eventually became our moon. Okay? So that collision occurred at least 4.5 billion years ago. Quick refresher on the scientific method. We've already talked about this a little bit today, but that scientific method starts off with an observation. What's the next step? I observe something. If I wanted to apply the scientific method, what's my next step? My hypothesis. Yeah, so I've seen something happen and I want to justify why it happened in the first place, right? So I make a hypothesis for it. Now, there's no way for me to know if that hypothesis is true. It's just conjecture based entirely upon observation until I can prove that it is true. So what do I do next?
You test it.
I test it. What's the intention of my testing? What am I trying to do? I'm trying to prove my hypothesis, so I want my hypothesis to be right.
Or you're
Or
trying
no.
to prove it's wrong.
This is the trap. That's what you would think. We all want to be right, but those who are truly scientifically minded care a lot less about being right and more about finding what is right, what is true. Whether that means me being true, someone else being true, or not, right? Because if I develop a hypothesis, and then I do every test possible, and I prove it wrong, I've still found truth, right? The truth I have found is that this hypothesis was not correct. The universe says no. Okay? So, I am not attempting to prove myself right, I am rather attempting to find truth, and the best way to do that is try and prove myself wrong. By trying to prove myself and my hypothesis incorrect, I circumvent that funny little thing called bias, which is my innate desire to prove myself right. So, if me and my team try and prove myself wrong, and we succeed, congratulations. If we don't prove ourselves wrong, congratulations. In both cases, truth potentially achieved. Okay, that's called falsification. Very important concept in scientific method. Unfortunately, it's kind of fallen by the wayside these days. If it survives this hypothesis testing, then your hypothesis becomes a theory. Okay. Quick refresher on the rock cycle. We have magma. Magma crystallizes. It crystallizes into what type of rock does magma become? Igneous rock. Thank you. That igneous rock is exposed at the surface. It weathers down. It turns into sediment. That sediment is deposited, lithified, and becomes sedimentary rock. The sedimentary rock gets buried deeper over time, goes through heating and pressurization. It goes through another process and becomes metamorphic rock. That metamorphic rock can get buried deeper underground, remelts, turns back into magma, and our cycle continues. With, interplay that happens between and in there and all of that, igneous rock can immediately be metamorphosed. It can be immediately remelted. There's a lot of combinations that can happen there. But that's your general rock cycle there. Now, as we go through this class, I'm going to be referencing different layers of rock with different names. And we have ways of classifying layers of rock apart from each other. It's a nested hierarchical group, you can think of it. Okay? It's a good way of putting this. Think about this for a second. Yeah, this will work. You are a student in a classroom. This class is part of a graduation body, okay? You're all generally going to graduate at around the same time, okay? And probably in the same academic year. You are then going to be part of a much larger group called the alumni of Odessa College. That's kind of a nested hierarchical structure, okay? Going from a small group like this to a larger group that you were a part of, and then an even larger group than that. Think of rock bodies in the same way. We have formations. A formation is a distinct groupings of rock. Within each one of those is a member. So I can have the Sergio member of the Jared formation. I'm just throwing names up there, okay? Now, why are we differentiating them from each other? Okay? Well, maybe this member, oh man, that color difference is not showing up very well on here, is it? I have the member as a very darker red, which is showing up great on my PowerPoint, but not so much on my screen here. Okay, but this is supposed to be a much darker color there. That member may represent one thing that happened in the environment. Maybe for a small period of time, there was a desert that migrated through. So this is a cross-bedded sandstone. As part of a larger group called a formation, which represented a general drying trend in the area during the time that that sediment was being deposited. Okay? I have designated this formation because it represents something that happened in the environment in those layers of rock. And this member is one aspect of the thing that happened in that time period. The formation, in turn, is part of a group. So perhaps this group represents a bigger, longer-term change. So if this member represents a period of desertification, and this formation represents a period of overall drying, maybe this group represents a cycle of increased aridity and then increased humidity, and then increased aridity and increased humidity, going back and forth. That group then is also part of a larger supergroup, within which it represents a smaller component of whatever the larger supergroup represents. Okay, so overall, what we're recording in layers of rock, what we're interpreting, are the environments of the past that occurred while the sediment was being deposited. Because small things are part of large things. We need a way of expressing in geology what the larger trends are and what the shorter term trends are. And that's what this is supposed to show, okay? Members are part of formations, formations are part of groups, and groups are part of supergroups, and they all are meant to be separated from each other depending on the trends that we observe in the layers of rock. Are we following this okay? Are we dead? We're a little dead? Let me help this. What?
Nothing.
Nothing?
I just have a feeling.
You got it back.
One of those-
Do I have a fact? Do I have a fact? Yeah, I've got tons of facts. Would a fact help wake you all up? Okay. Would you rather have a fact or a dad joke?
Dad joke.
Dad joke? Oh man, that was fast. Jasmine's been facted out today.
Well.
Well.
My feeling was correct. That I know.
All right. So, someone's been putting extra dirt in my garden. The plot thickens. Thank you. Okay, good. Little more awake now. Feeling more alive. With top tier humor in your ears. All right. Well, let's finish off with this thought then. Earth is a very unique place. It's pretty special. We like it here. Based on the size of our universe and how many planets we can actually see, if you take that number of planets that are within our visible area, multiply that by the rest of the universe, assuming that the ratio is going to be the same, that's how many potential planets there are in our universe. What number is that? Let's figure it out. Well, that's hundreds, thousands, millions, billions. What comes after billions? Trillions. What comes after trillions? Quadrillions. What comes after that? Quintillions. Yes. Okay. 700 quintillion planets in our universe. What a number. Now, our planet has a lot of things going for it. It's got the water, it's got the atmosphere. And the interaction of water, atmosphere, and geology makes things like soil, which allow plants to grow here. We have a lot of stuff going on. If we assume that our planet is one, what do you think? Is our planet 1 in a billion? We say 1 in a billion. If we assume that our planet is 1 in a billion of other planets. Well, let's see. 1 billion. That still leaves hundreds, thousands, millions. If we assume our planet is 1 in a billion, that means that there are 700 billion planets like ours out there. Each of which has just as much potential to have life just like Earth does. How cool is that? Now, we already talked about this. Light. Speed of light is our ceiling. Will we ever see any of those planets? Probably not. Is the potential that we see those planets now? Very. There's actually a really cool fact here. In our galaxy, we have caught glimpses of planets around other stars. And there's this really cool thing called spectroscopy, which the light reflected off of an object comes to us, we absorb it through our detectors, and then those wavelengths of light, because we know what elements reflect different wavelengths of light, we can see what that planet is made out of. There are planets that through spectroscopy we have identified as having atmosphere and water. Gosh. They're like 80 light years away. Pretty untouchable for now. Even if we made that theoretical 1/10 the speed of light engine and launched it today, it would take 800 years to reach that world. Yeah.
But then still, what if we talked about like the way that light or the speed and time went together, it would take 800 years here. But for the people, we're going to over 80 years.
Yeah. Oh, I mean, yeah. Only 80 years would pass on that ship. 800 years here, though.
800 years would just be.
Right. Well, actually, not 80 years. It would take 80 years. Okay, so if they're traveling 1/10 the speed of light, time slows down approximately 10. It's not a perfect ratio, but about 10%. So it would actually be 90% of 80 years that they would experience. Of 800 years. So that ship would still experience like 720 years or something like that. It's not perfect. I did the math in my head, but 800 years would pass for the rest of the world. Have you guys ever read a book series called Ender's Game? Have you ever heard of this? By Orson Scott Card. Very, very well-known science fiction novel. He actually did a great job of incorporating this. This guy, the main character, his name is Ender. He ends up, spoilers I guess if you haven't read it yet, but it follows him going from a kid to an adult. And he's this guy that he gets in a ship and then he'll travel from one world to another through the empire of humanity out in the stars. And hundreds of years will pass between when he goes from point A to point B, and he'll be the same age when he arrives because he's traveling at the speed of light. But humanity will have progressed hundreds of years. He will have gone from being a very prominent figure in civilization to arrive there. People will have not forgotten about him, but he'll have become a legend, a myth that's passed from generation to generation. And then he'll show up in another world, he'll have some kind of adventure, make a name for himself, and then he'll go on to the next one. And then he'll arrive there X number of years later, and he will have become myth again. So, very, very interesting concept, which is very, very true scientifically for the most part, okay? What are we talking about? Oh yeah, the likelihood of getting to these places. So we can see these worlds. Earth-like worlds, we call them. Because they are within the same distance from their star that Earth is from ours. They have liquid water and an atmosphere very similar to ours. Is anything living on these things? Can't tell that from a spectroscope. Not unless they had infrastructure in space that was large enough to reflect back at us. And we can't detect that yet. Potential, maybe future technology, but not yet. But we know those worlds are out there. We know that, at least from what we can see of them visually right now, they are capable of sustaining life like Earth is. Just don't know if there's life already on them. Likely? I think so. I find it extremely likely that there is life on other worlds. If our world, the exact way that it is 1 in a billion, and there's 700 billion of them, And if we even assume that only 1 million of that 1 billion has life, then that's 700,000 worlds just like Earth, with life on it, civilizations just like ours. So statistically, yeah, it's impossible that there isn't more life out there. And that's on a world just like ours. Life can develop in so many ways, guys. Right? There's the potential for life almost anywhere out there. Fascinating to think about. Okay. Any questions about that? No other thoughts? Comments? Jokes?
You think that on another planet right now, they're thinking about us too, thinking about like, hey, you see that planet over there? It looks kind of like ours. You think there's life over there?
Yeah, I think so. So are they looking at us right now through a telescope thinking, oh man, that one might be capable of life just as easily as us looking at theirs, right? But here's the time thing again, right? We're looking at a world 80 light years away. We're looking at it 80 years ago to their perspective, right? Someone looking at Earth 65 million light years away is looking at Earth that's covered in dinosaurs right now. They have no idea we exist because they can only see the light that's reflecting off of our world, and right now our world is reflecting the light to their eyes that's 65 million years old. To our perspective, right? Light is a tricky thing to work around. Which is why it's not as simple as simply going to another planet, guys. You gotta take the math into account. That planet I mentioned, that's like maybe 80 light years away. If we were to launch a ship and go there right now and it arrived in 800 years, we don't know where that planet is in 800 years. That planet is orbiting its star. That star is orbiting in a star system around our galaxy. Our galaxy is always moving. Our galaxy is moving, 200 million miles a second? That's how fast our galaxy is moving. So we launched that ship to try and get to that planet right now, and we don't know the trajectory of that planet. Our ship might just end up in outer space somewhere. We need to know a lot more and have a lot better technology for mapping these stars and knowing where their orbits are before we launch anyone out of our star system to get there. We've only ever launched 2 things outside of our star system. Voyager 1 and Voyager 2. Both of them were launched 50 years ago next year. Next year is the 50-year anniversary. They were launched in 1977. I'm actually planning a big community education event around the Voyager spacecraft so we can celebrate the 50-year anniversary of their launch. Because people have kind of forgotten about them, and I think they need to be remembered because they're the only objects that humanity has ever made that has left our solar system. They're out floating in deep space right now. And each of them contains a package, which is essentially a greeting.
The golden disc.
The golden disc. Yeah, each of them has a little golden disc on there that is a greeting to any extraterrestrials that pick it up. So, pretty cool. What's an even cooler concept is the fact that if we can actually progress our technology and build that faster engine, we could leave our star system and go past the Voyager spacecraft on our way further out into space. Maybe in 50 years from now. So 100 years after launching the Voyager, we will pass them because of the nature of the speed of light in space. Cool thought. Okay. Any other questions? Alrighty. Well, I'm going to end the recording here. We'll stop the class. I don't have a lab for you today. I'll be giving you your first lab on Monday. So this class meets Monday, Wednesday. Excuse me. So you'll get your first lab on Monday, and then your second lab probably the following Monday. Okay? We have Easter this term, but we don't take Easter Monday off, I don't think, do we? I think think they close campus for the Friday before Easter, but I don't think we take the day after Easter off. So I don't think we actually have any holidays this term that will mess up our class schedule. Not off the top of my head. So that's good. Okay. Well, for my online students, if you have any questions about what we talked about today, please leave it in the Go React comments or shoot me an email if you can't figure out how to make that work, and we'll get it straightened out.